At the architectural scale, this research takes the high-density scenario as a critique of modern-day urbanization that is shaped by an assumed unending abundance of energy sources and the short-sighted reliance on private vehicular transportation. This research aims to achieve a model of urbanism that is 2 to 3 times as dense as some of the densest cities today. One of the main issues in these high-density cities with urban blocks packed with skyscrapers is sunlight penetration to the ground. To tackle this problem, an optimal solar envelope is designed based on the annual sun path in the UAE, which blocks sunlight penetration after a certain time in the morning and before a certain time in the evening, and allows it to penetrate through at the other times. Similarly, it blocks afternoon sun in the summer but lets it penetrate during the winter. If this envelope is horizontally repeated to form a grid, it ceases to work as they block each other's light. But when the form is inverted to form a tripod-like configuration, it works successfully because it leads to continuous light shafts at regular intervals. This form can be stacked vertically to form a three-dimensional lattice, which can be parametrically diversified to achieve differentiation. This system is tested in Ecotect against a conventional field of vertical towers with approximately the same amount of built mass, and it proves to be drastically more efficient in terms of light penetration to the ground. To test the workable range of this system, various tests were done with height, thickness, and flow plate shape. The quad proved to be the most suitable flow plate shape structurally and aesthetically. The overall lattice worked best with angular variations between 45 and 60 degrees, and the towers could vary between 10 to 45 meters in width. An urban zone is designed and detailed using these limits to demonstrate the spatial qualities of the resulting architecture. The landscape is designed so as to shape the circulation network in terms of open spaces, plazas, and hierarchy of pedestrian streets. The street network is derived by a Voronoi algorithm with the touchdown points of the towers as the centers to optimize the landscaped area around each tower. The distance of the street from the tower determines the height of the landscape, which can lower down to create an access into the tower, or it can rise up several levels to become built area by itself, shaping and shading the streets. This creates low-rise buildings with extremely large floor plates that can be used for public programs such as institutions, commercial complexes, or auditoriums. Creating a cluster of intersecting towers over a large urban field opens the question of elevated pedestrian streets and elevated public spaces. To address the issue, large semi-public atriums are designed inside the towers at the connection points with elevated streets. This void is carried through to the height of the tower by a double skin system that creates a more open internal facade separate from the exterior. One of the primary challenges of building in the desert is that of minimizing direct incident solar radiation on the building skin. As the towers are inclined to optimize sunlight penetration to the ground, direct solar radiation is already reduced. However, to gain better control over the sunlight penetrating the buildings, a system of color mapping the sun path is developed to index the direct sunlight on the facades. The system maps a customizable gradient of colors onto the sun path, rendering the geometry with sunlight that takes its color from the specified gradient. For any given facade, this system provides detailed information on the angle and time of incident sunlight, shadow of neighboring buildings, and the degree of exposure. The color map can be customized to get seasonal information instead of daily information, or more detailed daily information in a particular season, or to map only the undesired sunlight through the day and year, or to study any particular time of the day in greater detail. This system outputs RGB color values mapped onto facades, creating an individual map for each facade. A catalog of generic facade components is created to block sunlight at specific times of the day: morning, noon, evening, completely blocked, and completely open. The color maps generated by the sunlight system are used to interpolate between these facade components, producing a facade that is completely adapted to the incident sunlight. The facades produced are not kinetic. They sample values of light in an incremental manner, gradually arriving at a final fixed state. The facade system registers structure by densification and thickening up of components along lines of structural load, and scales the opening up or down based on the programmatic requirement inside. The system works with a wide range of facade geometries, producing visually very diverse results that are functionally the same. The floor plates are designed to snap to lines of facade around the edges to maximize or minimize the amount of bounce light in the interior. This combination of the facade and floor plate system provides a very high degree of control over the amount of sunlight entering any interior space. This project is a research in parametric design methods applied to urban and architectural scales. As opposed to conventional methods of design where the outcome is a singular design proposal, this project focuses on designing intelligent computational systems that are capable of producing multiple iterated results responding to the changing input parameters. Some of these systems have been used in a bottom-up manner to achieve qualities of emergence and organic growth. If such techniques are applied to professional planning and architectural practices, they are capable of substantially expanding the scope of design possibilities and significantly reducing production and revision times, thereby resulting in better designs.